the next little shift in thinking is going to realize that if we have a vector field, so it's some formula times I plus some formula times j plus some formula times k, and remember that's just saying we have a formula for an arrow at every point, that there are 3 Green's theorems, not just one. So the idea is going to go like this. How do we get the 1? Right? Well, with the one we're used to, we draw x and y, we stick up a vector, and that vector is going to be k, and then what we do is we have a little tiny region, and we find the work done by that vector field around the vector k that's just sticking up like this. Now the thing about it is, k is just sticking up like this. All the work done is actually perpendicular to k, so as long as I stay in the xy plane, or actually just a plane that's parallel to the xy plane, right, what we're going to get is that the work done there is going to be exactly what we think it is. Partial f2 with respect to x minus partial f1 with respect to y times that area. I'm going to call that little area area 3 because it's actually perpendicular to k. That's what happens if we're in the xy plane. What happens if we're in the yz plane? Very similar thing. I want a teeny tiny region. I want the work done around that. What I want to do is just write down the sort of thing that's parallel to that, because what we're really doing here is we're sticking out a vector that's perpendicular to this. Right? Well, this vector this time is going to be I, and we're going to see what work is done in that plane, the yz plane, or any plane that's parallel to the yz plane. Now, since it's perpendicular to I, f1 is not going to even come into play. So what we're going to get, I think, is, let's see here, if I do this right, this should be something like f3y, and so I'm just thinking vertical, horizontal, which is what I did here, vertical, horizontal, right, minus f2z, and so that's horizontal, vertical, times this area, and I'm going to call this area a1 because it's actually perpendicular to I. So this is what the Green's theorem in the small or locally would say about a little tiny region that's parallel to the yz plane. The third one's very similar. You would think I would go like this and call this xz, but I'm not going to. We want to actually say the right-hand rule, and if we're actually looking at this, our first picture started with x and went counterclockwise to y. Our second picture started with y and went counterclockwise to z. And then our third picture has to start with z horizontally and go counterclockwise to x. So if I'm going to be consistent with the way I'm writing down other stuff, this has to be z, this has to be x, and then we can write down what this little piece of Green's theorem will say about a little tiny region in the xz plane, or really anything that's parallel to the xz plane. What we're going to do is stick out a vector here, but now this vector is going to be j, and we want to find the work done around that stuck out vector. And what we're going to get, because this is just a Green's theorem, but focusing in just one place, we should get something like, I think, partial with respect to of f1, so it's vertical, horizontal, minus horizontal, vertical, like this, times a little area, and I'm going to call this area area 2 because it's actually perpendicular to j. So this is what Green's theorem locally says about regions that are actually parallel to the xy plane, or parallel to the yz plane, or parallel to the zx plane. And the sad thing is, right, is that each of these formulas has to come into play when we actually do our formula, because in 3D, all three are going to play a part.